In this lecture, we're going to do a few things. First off, we're going to do a quick review of internal forces, in case it's been a while since you watched the last video. And then we're going to just do some more practice problems so you can really hammer home these concepts and see how they're applied to ENES 102 problems. So everyone, take out your safety scissors and get them ready, because it's internal forces time! Now remember, what are internal forces? Last time we explained that internal forces are all the forces that we don't see, but that are happening inside of the structure to keep it stable and upright. So in this particular case, the way that you always handle internal forces is you want to make a cut at the point you want to figure out what's happening. Hypothetically, let's say that that's point D in this example. The next step in an internal forces question is always to decide whether you look to the right or you look to the left. And remember, you always want to look to the spot that has the fewest unknowns. In this example, when you cut and you look to the right, you got nothing going on. When you cut and you look to the left, you see an applied force of 20 newtons and you see all those reaction forces at the fixed support. So you ignore all of that and you just keep it and you look to the right, because that's going to be the easier solution path. In internal forces, remember that every time you make a cut, effectively what you've done is you've created a new fixed support. So there's going to be 3 reaction forces that you have to always draw at every cut you have. That's going to be a normal force, P, a shear force, V, and a bending moment, M. You always want to draw them in the positive sign convention for the internal loads. That's shown below. You can keep one of these on your formula sheet, and it'll help you always keep things together when you start off on the problem. As I was saying before, this sometimes can be a little confusing, the sign conventions, but as we go through the problems today, I think it'll all become a little bit more clear and you'll see what's happening. Now, everybody, get ready, because it's time for some practice problems. Get those glasses out. It's practice problem time! I want to start these practice problems off with a question to you, which I can't see you right now because I'm wearing these silly glasses. But if I remember correctly when I made these slides, the question is, what are the internal forces at this particular point of the beam, which you can see is a cantilever beam with a triangular distributed load? What I want you to do is pause your video, not laugh too hard at me wearing these silly glasses, and I want you to figure out what are going to be the steps you need to follow to solve for the internal forces in this question. Where should you make the cut? Which side should you keep? And then roughly, what are you going to do? So pause your video and think through those steps right now. Now that you've probably had a little bit of time to think about it, let me walk you through the step-by-step process to do every internal loads problem that you'll ever see. Step number 1. Draw a dotted line through the point that you want to make a cut through, where they ask you to solve for the internal loads. In this question, that's point C. So we draw our red dotted line. Question 2 that we need to answer is, do we want to look to the left of the dotted line, or do we want to look to the right of the dotted line? The way to figure this out is basically to figure out which of the two sides looks like it's going to be easier to solve. By that I mean, you always want to try and avoid looking towards a support. So if you can look away from a roller, a pin, or a fixed support and not see it, you should definitely do that. But if you do see a support, try and make it the one with the least reaction forces. So if you have a pin and a roller in the problem, you should almost always look at the roller, because that has only one unknown force, whereas a pin would have 2. So look at the spot that's going to be easier means look at the side that has the least amount of forces and unknowns. The next thing you want to do in the trying to make it easier section is try and avoid distributed loads, and especially trapezoidal distributed loads if you can, because that just makes it even more complicated. There's more steps that you have to do. So after you think through all those things right there, part 2, A, and whatnot, you decide which side you want to keep. Now for this question here, you definitely want to look to the right, because if you look to the left, you see a support. That's tricky. If you look to the left in this question, you also see a trapezoidal distributed load. That's also tricky. So this question here, you look to the right because there's no supports and there's no trapezoidal distributed load. Now these rules are not always true, but I'd say a good majority of the time, those two rules will be true and will help you solve the problem as quickly and efficiently as possible. The last step we need to do is, hypothetically, sometimes you might need to look towards the support. So if you included a roller or a pin, before you can solve for the internal forces, you need to look at the whole structure itself, solve for the external support reactions at that roller or at the pin, whichever one you're including in your free body diagram, and solve for those, and then you can actually make the cut and draw the free body diagram of the cut section. And always remember, and this is tricky, I think it's a mistake that lots of people make, it's that when people make a cut, they already had solved for the equivalent distributed load force. So what I mean by that is, like, if you look at this question right here, what you want to avoid doing is you want to avoid starting off the problem by saying, distributed load. It's a triangle, here's the distributed load. Because what that would do is every time you cut the structure outside of that point, you would see nothing going on. But that's definitely wrong. Because the triangular distributed load acts over the whole system, what's actually happening is that every single part of this beam along the whole length of the distributed load is carrying force inside. So you always want to include the distributed load in your cut and then solve for the equivalent force. And you'll see this as we go through some of the examples in the next few slides. And pretty much last but not least, the final step is you want to make sure that when you make the cut and you keep the sides you want, you draw all of the internal loads there in the positive sign convention as was shown on the previous slide. And then you're ready to go. Use your sum of the forces in the x, y, and z, the moments, to solve for the internal forces at the points you've been asked to solve for. Now let's look at this example here. The question asks us to solve for the internal forces at point C. So our first question should be, alright, let's draw a dotted line through C and figure out, do we want to keep the left or do we want to keep the right? As I explained before, in this question here, we are going to want to keep the right side of the cut. And the reason is so we can avoid the trapezoidal load and so we can avoid the reaction forces at A. Once we cut there and draw the free body diagram of the beam and the triangular distributed load, the next thing we need to do is to figure out how to replace the triangular distributed load with an equivalent force. Now what's tricky is that we've cut our triangular load kind of randomly, so we don't know what the height is anymore. Let me show you how you go about solving for what the height of the triangular distributed load is at the point that you've cut, in this case, point C. So effectively, what you have is a graph. The triangular load starts at 1200 tall, and that goes over a span of 3 to the height of 0. So as you may have probably guessed, you can use similar triangles or your basic equations of slope to solve for the point that you need. Effectively, what we're doing is we're saying, hey, we want to solve for the load at 1.5 meters. And the way that we do that is we can say, similar triangles, 1200 over the height is equal to 3 over 1.5. You could also use the rise and the run and write a slope equation. And what you'd ultimately find is that because we're in the middle of the triangle, we have a height of 600. Now we don't always get this lucky that we're right in the middle, but this is the methodology you can use to figure out the height of the triangle through the point you cut. Because we can't use 1200, that's how tall it was at the far end, we need to use in this problem 600. So now that we've done that, I'm going to jump to the handwritten solution and show you how to calculate all of the internal loads at point C for this particular example problem. Now in this question right here, we have another question that's asking for us to solve for the internal forces at point C, right here in the middle of this beam. So again, get your scissors, but be safe, don't go running with them. We're going to try and take our scissors and we're going to make a cut through point C. And we're going to figure out what are the internal loads at that point. first question is, which way do we want to look? Do we want to look left or do we want to look right? Well, you don't have to be a rocket scientist to figure this out. If you look to the left, we see distributed load and a fixed support. That's going to have 3 unknowns. That makes us sad. If we look to the right, we see only the distributed load and no reaction forces at B, because this is a cantilevered beam. So what that means is we're going to be super lazy and smart, and we're going to cut and look to the right at point C. The next step would be then to draw a free body diagram of this segment right here. So I'll do that right now. Okay, now drawing the free body diagram, we can see that we've got point C down here. We're going to have 3 internal loads because, again, anytime you make a cut, it's a fixed support. So we see VC going up, our Y force, PC, our normal force or X force going to the left, and our moment going this way. Again, just to reiterate, I've drawn all 3 of these internal loads in the positive internal loads convention. However, PC is drawn to the left, so it's negative in our calculations, and MC is clockwise, which is also negative in our calculations. The only thing that we don't really know is I've drawn the distributed load that we see to the right, but we knew that at the top it was 1200. It was a triangle, and it went to 0. But we don't know what it is here. Well, how do we solve for that? Well, one way you can do it is similar triangles. So what we can see is that our triangle that we started with was 1200 in height by 3 down here. The new triangle that we've cut through bisects that side, and it's 1.5 and question mark height. So the height of this, when we look at similar triangles, 1200 divided by h is equal to 3 over 1.5. Therefore, h is equal to 600. So what we need to do is we need to solve for the f equivalent of our triangle. It's going to be equal to 1/2 the base times the height, which is going to be 1/2. Our base is 1.5 meters, and the height is 600. So 600 divided by 2 is 300 times 1.5, 450. Now, just like as we've done many times before, this is our equivalent load. We need to locate it onto our free body diagram, and we're going to put it right here, which is the center of the triangle, center of mass, and that is at 1.5 over 3, or 0.5 from the left edge. Now we know everything that we need to know, and I'll just draw this 450 up here, just so we're on the same page. Now we know everything we need to know, so we'll sum up all of our forces. So we sum the forces in the x direction, set that equal to 0. That gives us PC negative. Well, that's it. That's all we have. Therefore, we have no normal force. Our beam is not in tension or anything yet. So we're good to go there. I promise you one day this will actually be something, but not yet. Now we have some of the forces in the y direction. Set that equal to 0. That's going to be equal to our VC going up, our shear force, minus 450, which is the equivalent load of our triangle. Well, that equation is pretty easy to solve. What we see is that VC is equal to 450. And because we drew it up and we get a positive answer, this is a positive shear due to sign conventions. Essentially meaning that it wants to move the beam up on the left and down on the right. So like that. Now we do some of the moments. We're going to do that about point C, the point we've cut. We'll set that equal to 0. Our MC is drawn clockwise, so in our typical math, we say that that's negative. So you got negative MC minus the 450 times 0.5. And here we've got our force. Here we've got our distance. Here's our moments. And this is also going clockwise. So what you can see is going to happen, and because we have two clockwise moments, this is drawn incorrectly in our free body diagram. What we end up getting is we get that MC is equal to 225 Newton meters counterclockwise. But technically, if the moment was drawn this way, in the opposite way that we draw it in the free body diagram, that would cause our beam to frown. So because that would be causing the beam to frown, then what that actually means is that MC, our final answer, has to be negative 225 Newton meters. That's a negative bending moment, because it causes the beam to frown. Now, I oftentimes get the question, Mike, am I going to fail this class if I have the wrong sign in the end when it comes out? My answer is absolutely. You should definitely fail the class if you don't know this. I'm just kidding. I usually mess with people. But the idea is that, no, I mean, if you get this wrong, I don't really care. Sometimes it gets confusing, but just do your best. If you get the wrong sign, not a big deal. But that's how we approach this internal loads problem. Now we're going to look at this problem here, and it is a doozy. It doesn't ask you for one, but two internal forces at point C and point D. And if you just can see what's coming, when you look at point C, if you make a cut there and look to the left or to the right, you're going to have internal forces and external forces involved. So you're going to have to draw a free body diagram of the whole system. That just means a lot of extra work. So let me go to the handwritten solution and show you step by step, methodically, how to solve this type of internal loads problem. Let's look at this internal loads example now. Now, if you haven't yet eaten your lunch, or you haven't gotten a drink for a while, please go get yourself a couple different meals, probably breakfast, lunch, and dinner ready, because this problem here is going to be a two-parter. It's a doozy. You can see already that there's lots of stuff going on, and our question that it asks us is to solve for the internal forces at point C, right here, and at point D, right here. So what we're going to do first is get out our scissors and make a cut. We're going to cut at C and D, and we've got to figure out whether at each point whether we're going to look left or if we're going to look right. So let's figure that out. Let's draw our red dotted line at D, and let's draw the red dotted line at point C. Now, point D is going to be the easier of the two to figure out. So if we look at point D, and we look to the left, we see a roller, a trapezoidal distributed load, oh no, and a pin. So that's going to be 1, 2, 3, 4, 5 things that we've got to figure out. If we look to the right, we see one thing. Woohoo! So you could, if you're really adventurous and bored and you're like, wow, I got all this food now, I'm ready to really hunker down, you could cut and make a look to the left. But you really should look to the right, especially at point D. So that's what we're going to do. Just looking at this question, it already seems very straightforward to make some cuts and look at point D because there's really only one thing going on. So I'm just going to ignore looking at everything else for right now, and I'm going to look at just this point right here. So we're going to make our cut, and we're going to draw a free body diagram of segment D. I'm going to do that right now. So, drawing the free body diagram of our cut at point D. Got that point labeled down here. So we've got 5 feet, and we've got our force over here inclined at a 5, 12, 13 triangle, and I've got my XY axes. So, I've drawn the 3 reaction forces for internal loads over here. They're all in a positive sign convention. The VD is going to cause the beam to go up on the left and down on the right, so that's positive. PD is in tension, and our MD is causing things to smile. So I'll sum up all of the forces here. Sum of the forces in the X. Set that equal to 0. That's going to be equal to negative PD minus 690 times 5 over 13. We want the X component of that. Now if we look at this right here, this is going to tell us that PD is equal to 265 pounds. But what we actually find out is that really it's a negative answer. So we get PD is negative 265. That means that PD should have been drawn the other way. If that's the case, if PD was pointing this way, and you were this piece of bar, you would feel PD pushing this way, and you'd feel this force pushing this way. Well, at that point, you'd be getting squished. So you'd be experiencing compression. So compression is considered a negative normal force. And again, because we drew PD in the positive sign convention for internal forces, when we get a negative answer out in the end, that means it switches our arrow. It should be pointing to the right, but when it's pointing to the right, that means the beam is in compression. If you're still a little confused on that, there's more examples. I think eventually it'll start to make some sense. After we've done some of the forces in the x, we'll do our sum of the forces in the y direction. We'll set that equal to 0. That gets us VD, shear force pointing up, minus 690 times 12 over 13. Now, you can see that this is going to get us a positive answer. So we get that VD is equal to 637 pounds positive shear. Again, because we drew our shear force going up, it's a positive shear, and because we get a positive answer, that means our arrow is correct, and we get a positive internal load convention out. Last but not least, we sum the moments about point D. We'll set that equal to 0 here. That's going to be negative MD because that's going clockwise, minus 690 times 12 over 13. We only the y component of this force. That's going to be pointing this way. It's going to cause everything to rotate clockwise. So we have 690 times 12/13 times the distance of 5. And this is also going to cause things to rotate clockwise. So what you can see is going to happen is because we have these two clockwise moments, we drew this one wrong. So really this moment here should be going the other way. That would cause the beam to frown. We would get a negative bending moment. So at the end of the day, what we get is MD is equal to negative 3,184 pound-foot. And this is a negative bending moment. And again, because we drew it in the positive internal loads convention, when we get a negative answer out, that means that we get a negative internal loads convention as well. And that's why you always want to draw things like that, at least in the beginning. Now, the next part of our question is solve for the internal loads at C. So, we have to decide whether we want to look left or whether we want to look to the right. Well, if we look to the left, we see a trapezoidal distributed load, an AX and an AY. If we look to the right, we see a roller, a trapezoidal distributed load, and this force here. Now, you could make the argument that we've got 1, 2, 3, 4 things to do if we look to the left, and 1, 2, 3 things if we look to the right. It's actually going to be easier to look to the right. Even though the number of forces are about the same, the number of unknowns or things to do is less. AX is a thing that we don't know. Whereas at B, we don't have an X component. So you usually, when you make a cut, you want to look to the right towards the roller. And if we do that, that means that we need to know what BY is, because that's going to be in our equations for the internal loads at C. So what our next step is to do is to actually draw this section of the beam here, draw the whole beam and solve for BY. And I'm going to set up a free body diagram for the whole beam and get us started to solve for this reaction force, because it has to be included in our drawing on the next part. Okay, so now I've drawn a free body diagram of the whole beam. I've got AX and AY for the pin at A. And I've taken this trapezoidal distributed load, and the reason we know it's trapezoidal is because you can see that it's got a triangle on the top and a rectangle on the bottom. So what I've gone ahead and said is, okay, we're going to have a rectangular load, F rectangle, and that's going to be located at 15/2 from the left, because we see that the distributed loads are 15 feet wide. So we're going to have 15/2, and then this triangle we're also going to have right here, sorry it's a little smaller, is going to be a 15/3 away from the left side because it's 1/3 of the way down. And I'll draw that up here just so it's a little bit more clear. So we have F rectangle at 15/2. And we have F triangle, draw it here, at 15/3. Now, what we need to do is we need to solve for BY. This is the most important thing that we need to be able to make our cut and look to the right. So if we want to solve for BY, the easiest and fastest way to do that is to do a sum of the moments about point A. Because if we do that, we'll get everything out of the way and be able to do it really quickly. The first two steps we need to do that is to solve for F of the rectangle, which we can see is actually going to be 40 pound per foot times 15. So we multiply 40 pounds per foot times 15 foot, and we get that F of the rectangle is equal to 600 pounds. And we do F of the triangle is going to be, well, 60 minus 40 is 20. So we get a height of the triangle load is 20 pounds per foot. And this is a common misconception. Some people go, oh, the triangle's 60. But no, the triangle's really the difference between these two, which is 20. So we have 20 pound per foot times 15 feet times 1/2. Because it's a triangle, it's 1/2 the base times the height. So we get that F of the triangle is 150 pounds. So once we have those two things right there, we do a sum of the moments about point A. The sum of the moments about point A is going to be equal to 0. It's going to be equal to the triangle, 150 times 5. It's 15/3. And let's go in clockwise. Minus the F of the rectangle, which is 600, times 15/2. That's also going to cause things to rotate clockwise. Then we have BY going up. So we say plus BY times 15. And now we have to account for the Y component of this force right here. And that would cause things to rotate clockwise as well. So we'd have minus 690 times 12/13 times, well, how far away is that from A? That's going to be 10 feet plus 15 feet, so times 25 feet. You can see that the only thing we don't know here is BY. So we can solve this equation right here. A bit of math. We get that BY is equal to 1,411.54 pounds. Bazinga. Okay, we've done all of that work, and we haven't even gotten close yet to doing the sum of the internal loads at point C. But now, the whole point of solving for BY was so that we can make our cut and we can look to the right. And I'm going to get a new piece of paper and we'll continue. All right, now we've got our new sheet of paper. I've shown the cut is going to be to the right at point C. I've put down that from the last page we learned that BY was 1411.54 pounds, and I've got our free body diagram at C all drawn over here. Everything should be pretty straightforward, but remember that this right here is a trapezoidal load, so what I need to do is have both a rectangular and a triangular component. Given that this distance right here is 3 feet, what I can see is that the F of the rectangle equivalent will be 1.5 from point C, that the F triangle will be 1 foot to the right from point C. So my first step is to figure out what is the F of the rectangle and F of the triangle. Well, remember that kind of the way that I went about doing this before was that F of the rectangle is 40, right? 40 just goes from the left to the right. So F of the rectangle is going to be equal to 40 pounds per foot times the distance that it acts over, which in this particular case is 3 feet. And that's going to be 120 pounds. F of the triangle is a little trickier to figure out, but what we can do is essentially use similar triangles. So what we can see from similar triangles, this is probably my favorite way to do it, is we see that we've got a big triangle that's 20, that 20 height right here, 60 minus 40, the 20 goes over a span of 15 feet. So we've got 20 over 15, and the triangle that we're looking to solve for is 3 feet with an unknown height. So it'd be 20 over h is equal to 15 over 3. So what we really want is h. So if we've got 20 over h equals 15 over 3, then what we get is basically that h, height of our triangle, is going to be 20 over 15 times 3. So we know that f triangle is 1/2 the base times the height, which is going to be 1/2 the base of our triangle, which is 3 feet, times the height, which is this, basically, which is kind of a lot, 20 over 15 times 3. And what this gets us is that the f of the triangle is a whopping 6 pounds. Whew. Thank God I just did all that math for 6 pounds of force. Now you can already tell, like, this isn't going to have much of an effect because it's 10 times, 20 times less than this force right here. So f of the rectangle is going to have a much bigger impact in this portion of the problem. But nonetheless, we still need to account for this. So now, after we've done all of this work, we can finally finish. We'll just sum up our forces in the x. We'll set that equal to 0. And that will be equal to 690 times 5/13, negative because it goes to the left. So negative 690 times 5 over 13 minus PC, because we've drawn it going to the left. What this tells us is that PC is actually negative 265 pounds, which is a negative internal load and means compression. Now do our sum of the forces in the y. Set that equal to 0. That's going to be VC going up minus F triangle minus F rectangle, which is going to be minus 6 for a triangle, minus 120 for a rectangle, plus BY, which is 1411.54, minus the y component of this force, which is 690 times 12 over 13. This tells us that VC is equal to negative 649 pounds, which is actually negative shear. So basically, the reason we get this answer is because our VC should be drawn down. And VC should be drawn down over here because it's almost like this force over here is causing everything to rotate that way. VC has to keep everything from wanting to rotate that way. So it pulls back down. And when we have a force that pulls back down in internal loads, what that does is it causes our beam to go this way, which just due to sign conventions is negative. So that's what we get there. And last but not least, we have to write our sum of the moments equation. We do sum of the moments about point C. We set that equal to 0. That's going to be our negative MC, which is a clockwise load that we drew right here. Then we have to take into account the rectangular force times 1, because it's 1 foot over, 1/3 of our 3 feet. That's clockwise. Minus the force of the rectangle, which is 120, and it takes 1.5 from the edge. That's also clockwise. Then we add in BY. That's going to cause everything to go counterclockwise. So that's plus 1411.54 times 3. That goes counterclockwise. And then we're going to have to account for this force right here, which is the y component will be going down, cause everything to rotate clockwise. So the y component of that force is 690 times 12 over 13. And we'll multiply this out by the distance from the right edge to our point C, which is 13 feet. And now we just have to solve for MC. So MC is equal to negative 4,231 pound-foot, which tells us that we have a negative bending moment here. And again, we drew our moment MC clockwise, which would cause this beam to smile, meaning in internal loads convention, it would be positive. When we get a negative answer, that means our MC should have been drawn the other way, which would cause the beam to frown. And when the beam frowns, you get a negative bending moment internal loads convention. There you go. That was the world's longest internal loads problem, and we finally made it through. Congratulations. That concludes all of our slides for the internal loads section. You'll find lots of extra resources in the PowerPoints that I've posted to our course website, and I hope you look through those. You get clear on all the concepts and get ready for your upcoming exam. Thanks for watching.